We've had a discussion about covalent bonding and looking at Lewis structures and seeing what kind of information we can get from Lewis structures. We've talked about ionic bonding from the point of view of those electrons and doing Lewis diagrams for it. We've talked about covalent bonding. What we need to be able to do is actually, from the beginning, construct a Lewis structure for either a covalent compound or for a polyatomic ion, because it will have covalent bonds within that polyatomic ion. Being able to construct this, I've seen a lot of times where students resort back to what they learned in high school and using those tools that they learned in high school. Your examples in high school were very simplistic examples. And if you try to continue to use that method, when we get into more sophisticated problems, that method falls apart. So try very hard to let go of what you've learned in the past and start with a new method that I'm teaching you here. Okay, I'm going to give you a process to follow, and a lot of times I'll see students not abandoning their old ways and then they get really stuck. All right, so constructing Lewis structures. First thing I have to here is to tell you that this is very important. By very important, I mean, what we learn here in these next few lessons about how to construct these Lewis structures, you're going to utilize throughout the rest of this chapter and all the way through the next chapter and into the next chapter and the next chapter beyond that. So you've got to really be able to first draw a good Lewis structure and then use that over and over again in other things, because it's pointless just to be able to draw a Lewis structure. You've got to be able to draw a Lewis structure and then get information from that Lewis structure. And it's getting information from that Lewis structure that we will do over and over again throughout the chapters to come. All right, so what I have here is a sequence of steps to follow. We're going to quickly talk through those steps because they're in your notes in their entirety. And then we're going to have them handy, I hope, for you. They're there by your side. So if you don't print off these notes, if you don't have the note packet, you need to take time to write them down. So you'll stop, start, stop, start, so you can write it down, because you're going to want them by your side as we do examples. Okay, so the first thing that we have to do is we have to, when we're given a structure, is know what the connections are. What is that skeletal structure of atoms and where they're going to lie next to each other as we start putting those electrons in. And there's some rules that we kind of follow for that. The first one is what goes in the middle. The least electronegative atom is going to go in the middle. Now when we write a formula, we almost always write the least electronegative thing first. So it's easy to figure out what the least electronegative atom is. Terminal atoms, the word terminal doesn't mean they're dying. Terminal atoms means they're the end of the train, okay? So the outside, the most outside atoms have to always be hydrogen, because hydrogen can only have one bond, and always has to be fluorine for reasons we'll get into. Another thing that we need to know is if we've got a compound that has multiple carbon atoms, maybe C3 carbons, carbons love to bond together, so most likely they will be connected as a chain. All right, that's the first one. The second one is to stop looking at that for a moment and start counting valence electrons. So you go to the periodic table, we know that the group numbers above them on the periodic table tell me how many valence electrons they have. We're going to count valence electrons, and we have to make sure we take into account a charge. If it's negatively charged, we're going to add extra electrons. If it's positively charged, we're going to take away electrons. The third thing that we're going to do, and this is where my method starts being different than what you might have learned in high school, is we just start putting those electrons in, okay? We have this pool of electrons to work with. We start putting them in. We put them in starting by connecting a central atom to its outside atoms, okay? And then you go to the terminal atoms, the ones on the outside, and you start making sure they have an octet satisfied. Give everybody 8 as you work your way around. You keep adding electrons until you use up that pool. And once you use up that pool of electrons, you have to stop. Now, at that point, you might be a good Lewis structure, but you might not be, okay? At some point, you have to stop adding electrons around. Now, if you do that and you stop and you run out of electrons and you look at your central atom and it doesn't have 8, then we have to start shifting electrons from the outside into making bonds, and we'll talk about that shift. We'll continue shifting until we make sure that everybody has got that octet satisfied. Then you're going to make sure that you've used the right number of valence electrons, that everybody has 8, and that will work. Now sometimes you give everybody 8 and there are still some electrons left over. We'll talk about that eventually, okay? But let's start doing some examples, all right? We're going to do several examples here. We'll do this on our board, and the first one that we're going to do is CH4, okay? So the first atom listed is almost always the least electronegative atom of the bunch. But regardless, we can't have hydrogen being the central atom. So we know carbon is the central atom and the hydrogens are surrounding it. So that's what I mean about deciding on the connectivity first before you ever put bonds in there. And now don't start putting bonds in there, and don't start putting dots for valence electrons in there. Go and start counting valence electrons, okay? So we look at a periodic table. I'll pull up, we're going to do all these, but let me pull up a periodic table. We find carbon on the periodic table, and the group number above it is 4. We know it has 4 valence electrons for the carbon. And for hydrogen, we have 1 valence electron, and there are 4 hydrogens, so that's 4 there. And we add the 4 and the 4 for a total of 8 electrons. Okay, so we have 8 electrons to work with. Then if you look at the rules, go back and look at those rules, it says start connecting the central atom to the outside atoms, the terminal atoms. Now I have 8 to work with, so I want to keep in mind that I can only use 8. So I'm going to connect this, that uses 2, then 4, 6, 8. I stop because I've used them all. I also stop because everything is happy, okay? Happy in terms of good energies by getting the octet rule satisfied. Now hydrogen doesn't have 8, but remember hydrogen's role model is helium. Helium is its nearest noble gas. So if you look at your periodic table there and find hydrogen, helium's right next door. Helium's element number 2, and that has 2 valence electrons. So every time hydrogen has a single bond, that's it for it. That's all it wants, it's all it can have. It's all it can handle, okay? We look at our carbon. Our carbon takes claim to these as well, so it has 2, 4, 6, 8 valence electrons, and it has satisfied the octet rule. So we've got our Lewis structure. Now, what students want to do from their high school days probably is to take carbon, look and see that it has 4 and draw 4 dots. Hydrogen, it had 1, and start pairing them up. And that will get you a good Lewis structure for this guy. It's just that down the road, it won't work well for you. So let go of that old method and start doing what I'm doing here. Now what was the next one I wanted to do? I wanted to do NCl3. So NCl3. The first element is going to be the least electronegative element. If you looked at a periodic table, that would bear out as well. So we have nitrogen with the 3 chlorines around it. Okay, doesn't matter where you put those 3 chlorines as long as they're around that nitrogen. Hold that for a moment and let's start counting valence electrons by looking at a periodic table. Nitrogen is in the family that has 5 valence electrons. Okay, chlorine has 7, but there are 3 of them for 21 electrons there. That means I have 26 electrons to work with. Now what's the rules next? Look at what you have there on your piece of paper and think about what's next, and then resume. Next thing is to connect things with single bonds using these electrons. I'm going to keep track of it. I use 2, 4, 6. Okay, I've given everybody a single bond. Now we need to go to the outside atoms. Don't worry about nitrogen. Go to the outside atoms and start giving them an octet. So I've used 6 so far, and then 8, 10, 12. That gives chlorine its 8. 14, 16, 18. That gives this guy his 8. 20, 22, 24. That gives this guy its 8. I still have some to work with, so I can move to my nitrogen. And it had 2, 4, 6. It needs 2 more, and that uses 26. Double check. Everybody has 8. Chlorine has 8. Chlorine has 8. Chlorine has 8. Nitrogen has 2, 4, 6, 8. Everybody has 8. And double check that you've only used 26. Those are the 2 things that should happen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I've got the octet rule satisfied, and I've used 26 electrons. So this is the Lewis structure of NCl3. All right, what was the next one we wanted to do? N2. All right, N2. Just two atoms, so they had to be connected to each other. So I've got a nitrogen connected to a nitrogen. Counting up valence electrons. Each nitrogen, if I look at the periodic table, each nitrogen has 5. So 5 times 2, I have 10 to work with. Now I only have 10 to work with, and somehow I have to make both nitrogens think they have 8. So there's probably going to be a lot of sharing going on, but let's use the rules and see how it works out. All right, the rules say start with a single bond. There's a single bond. Then go to the outside atoms. Well, either one is fine. I've used 2, 4, 6, 8. Now this guy is happy. I've used 2, 4, 6, 8. I come over here, use 10, and I have to stop because I've run out of electrons. It only has 10 electrons. This nitrogen's pleased as punch. It's got 8 electrons, but that nitrogen only has 4. So now we have to do the shift. If you look back at the rules, I say you're going to shift from the outside atoms in to try to make the other atom, and it's usually a central atom, but in this case it's this nitrogen, content, happy, getting its octet rule satisfied. All right, so what do I mean by shifting? If I take these 2 electrons right here, and I'm going to erase them, okay, and I put them here again, that's instead. I'm not using any more or less electrons. I've just taken those 2 and put them here. Now when I do that, let's think about what's happening to this nitrogen. He had 8. When I shift him here, does he not still have 8? Yes, he does. 2, 4, 6, 8. So he's still happy. Shifting doesn't make him unhappy. He still has that octet rule satisfied, but it's starting to make this guy getting where it needs to be. Right now this nitrogen has 2, 4, 6. Not quite there, so let's do that again. Let me take 2 more from this nitrogen and move it over here to share. So this nitrogen is doing more sharing. He still has 8, 2, 4, 6, 8. This guy now has 2, 4, 6, 8. So by doing that shifting and getting more sharing to take place, we are getting an ability to get both of them to have 8 valence electrons. Now let's do our double check. Does everything have 8, and have I only used 10 electrons? Well, this nitrogen has 8, 2, 4, 6, 8. This nitrogen has 8, 2, 4, 6, 8. I have used 10, 2, 4, 6, 8, 10 electrons. So you either getting the hang of it or you're not. If you're not getting the hang of it, I would recommend backing up and watching this again. Okay? If you feel like you're getting the hang of it, now it's time for you to try one. All right? So you're going to work on NO3 minus. And once you've worked on NO3 minus, actually, I want to kind of divide it up into questions. The first question you're going to answer is this one. How many valence electrons are in NO3 minus? All right, hopefully you got the right answer on that one, but if you didn't, let's talk through it. Nitrogen has got 5 valence electrons, right? 5 valence electrons for the nitrogen. The oxygen has 3 oxygens times 6. That's 18, but you have that minus charge. Did you forget about that minus charge? As you look and do counting up, if it's minus charge, it's because it has 1 more electron in there. So that is going to be 18, 19 plus 5 more, 24 electrons to work with. All right, so now you have 24 electrons to work with. You should have thought about how the connectivity occurs. You've got 24 electrons to work with, and I want you next to decide which one of those is the correct Lewis structure for NO3 minus. All right, so let's go to the screen here and let's say you picked 8, or you at least now know it is A. There's one last thing that we really should add to it when we're doing a Lewis structure that is not showing up on here and I haven't talked about yet, and that is that when you have an ion, you should put square brackets around your Lewis structure and put the charge outside of that. Okay? Now that A is the correct one. Now what's wrong with B? B uses the right number of electrons, but this nitrogen only has 6 electrons around it. Okay, so that's not a happy state for that nitrogen. So you use the 24 you were supposed to use, but that nitrogen's not happy. Well, here the nitrogen's happy, but you used too many electrons. This used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. And you can't use 26 electrons if you only have 24 to work with. So that's what is wrong with that one there. Okay. So what we're going to do in class is we're going to practice this some more. We're going to be giving you lots of examples to work on in your groups, to work on the rules, and for a while we'll have everything obeying the octet rule. Now remember, it's a rule. It is not a law. It doesn't happen every time, but so many things are driven by trying to get the stability of a noble gas that very, very often the octet rule is satisfied. And when you go on to, those of you who need to go on to organic chemistry, in the world of organic chemistry, that organic rule is almost always obeyed. And when it's not, it's really driving chemistry, and you'll learn what to do about it if it's not being obeyed, because organic chemistry will drive all of its reactions to try to get it to be obeyed.